Hi, so for today we're going to talk about transforms of derivatives, solving DE using the Laplace transform. And this is still a part of our lecture playlist in advanced engineering mathematics. So if you are new to my channel, please don't forget to click the subscribe button for you to be updated every time I upload videos in regards with the tutorial about advanced engineering mathematics and many math and engineering tutorials. So let's get started. So first, I will be showing you the formula, okay, the pattern of the transform of derivatives. So let me just read this. If f prime ellipsis f raised to n minus 1, where n is the derivative, nth derivative of a function, are continuous on the interval 0 to infinity, 0 inclusive and infinity exclusive, and are of exponential order, and if f raised to n of t is a piecewise continuous on this, again, this interval, then we have this formula for getting the Laplace transform of the nth derivative of a certain f of t or function. So we have the Laplace of the f raised to n, where n is the nth derivative. It can be first derivative, second derivative, third derivative, fourth, and so on and so forth, of t, okay, is given by this formula or this pattern, where we have s raised to n, where n is the derivative, and we have f of s, that's the Laplace of our f of t, Laplace transform of our f of t, and minus s raised to n minus 1. So we have the derivative and derivative minus 1 and multiplied by the f of 0, okay, or the initial condition can be the initial condition given, minus s raised to n minus 2 f prime, okay, of 0. And if we're going to continue this, we can see the pattern that the next term here will be s raised to n minus 3 f double prime of 0, and so on and so forth until we reach this one. So we have the nth derivative, and we have the definition of f of s as the Laplace transform of the f of t. So transforms of derivatives is also another way of solving a differential equation using the Laplace transform. So for us to see, okay, and learn this, we have to solve some examples. So for this video, I'm going to solve one example only of the order 1. When we say order 1, we only have the first derivative. Okay, so we're going to solve this. So use Laplace transform to solve the initial value problem. We are given a differential equation here, such that we have dy over dt plus 3y is equal 13 sine 2t, where we have an initial value given, y of 0 is equal to 6. So how do we solve this given DE using the transform, okay, Laplace transform? So first, okay, solution, we have the solution here. What are we going to do is to get the Laplace transform of this whole equation, differential equation, by using our knowledge in Laplace transform, and of course, in the Laplace transform of derivatives. So, as you can see here, we have a dy over dt. Okay? So, this is a first order. So, our n here is equal to 1. Is equal 1. Okay? So, we have n is equal 1. N equals 1. Okay? So, we have to get, okay, by properties of Laplace transform, okay, we can individually get their Laplace transform. So the Laplace transform of dy over dt, okay, let's say dy over dt, so that would be, from our formula a while ago, our n is 1, so we have s raised to 1. Okay, since the dependent variable here is y, so we have y of s instead of f of s. Okay, so we have y of s. This means that the Laplace transform of this. So, and then we have minus s raised to 1 minus 1. Okay, and then we have, okay, f of 0. In this case, that's y of 0. So we have s raised to 1. I won't mind writing again the exponent because it's actually understood that it is raised to 1. So s raised to 1 minus 1, s raised to 0 would be 1. So this would be y minus y of 0. So in other words, we are given y of 0. So the Laplace transform of this should be s of y of s minus 6 because y of 0 is equal to 6. So that's the Laplace transform of this first term. How about this term? We get the Laplace transform again of 3y. Okay. So we can factor out the Laplace transform or the constant, I mean 3 outside of the Laplace transform. So we have 1. So simply the Laplace transform of y, okay, would be simply y of s. So we have 3, okay, y of s. Okay. It does not have any derivative, okay? So it should be s raised to 0, which is 1. We have y of s. So the first term of this, okay, s raised to 0 is equal to 1, then we get y of s. Okay, which is this. It so happened that it has a 3, so we have 3y of s. So how about the Laplace transform of this? So we learned this from our previous video where I actually discussed how to get the Laplace transform of that. So we can factor out 13 outside of the Laplace. So we have sine 2t, okay? Get the Laplace transform, sine 2t, that's 13 multiplied by, sa Laplace transform, that's 2 over s squared, okay, plus 4. 13 times 2 is 26 over s squared plus 4. And what are we going to do? Okay, let me just box them, the Laplace transform of each term. What are we going to do is to simply substitute the values. Okay, rewrite. So we have the Laplace transform of dy over dt. That's s y of s minus 6. Okay, plus 3y of s, okay? And that is equivalent to 26 over s squared plus 4. So we have gotten the Laplace transform of this whole differential equation. So what are we going to do? We need to isolate y sub s. Isolate y sub s because that's the Laplace transform. So we need to isolate y sub s on the other side of the equation. So what I'm going to do is we have sy of s plus 3y of s. I'm going to transpose negative 6 on the other side of the equation so that we have 26 over s squared plus 4 plus 6. Then y of s is common to them, so I can factor it out. So we have s plus 3 is equal to 26 over s squared plus 4 plus 6. So divide both sides by s plus 3. So we have 26 over s plus 4, s squared plus 4, then s plus 3 plus 6 over s plus 3. So what are we going to do here? Okay, after this, we're going to resolve this into partial fractions because this y of s, we're going to get again the inverse Laplace transform of y of s. So to get the inverse Laplace transform of this, we need to resolve this into partial fractions. Okay? So in order for us to actually resolve this, let us first simplify this. So this y of s, if we're going to simplify this should be 26 times s plus 3 plus we have 6 times s squared plus 4 times s plus 3 all over s squared plus 4. Then we're going to multiply the denominator. So we have s plus 3 squared. So as you can see, s plus 3 is common to them. So I can factor that out. Okay, we have s plus 3. We have 26 plus 6s squared plus 4. Okay, all over we have s squared plus 4 then multiplied by s plus 3 squared. So as you can see here, this s plus 3 will cancel the denominator. So we have actually we call this simplified. So we have 26 plus 6s squared plus 24 all over, we have s squared plus 4, then we have s plus 3. Further simplify, we have 26 plus 24, that's 50 plus 6s squared all over s squared plus 4 and multiplied by s plus 3. So what are we going to do? We're going to resolve this into partial fraction. So resolve into partial fractions. Because we're going to get the inverse Laplace of that. So we need to resolve that into partial fractions. So what are we going to do? Let me just rewrite. We have 6s squared plus 50 all over s squared plus 4. Then we have s plus 3. So as you can see, this has a quadratic. This is quadratic raised to 2. So we have resolve it into partial fractions. So it's important for you guys to recall your partial fractions. So we have a over s plus 3, okay, distinct, and it does not have any degree, or I mean the degree is 1, so we have only a, and that is plus, okay, bs plus c, okay, because this is quadratic, s squared plus 4. So we need to solve for the values of a, b, and c. So if we are going to multiply this whole equation, okay, by the denominator here, s squared plus 4, then we have s plus 3. So simply we will be having 6s squared plus 50 is equal to a, okay, times s squared plus 4 times s plus 3 all over s plus 3, plus we have bs plus c. Then we have s squared plus 4 times s plus 3 all over s squared plus 4. I've shown you the step by step. So this s plus 3 would cancel, this one and this one also. So we are left with a times s squared plus 4, plus we have bs plus c multiplied by s plus 3. So we need to get the values of a, b, and c. Okay, so we have as squared plus 4a, distribute that. This is foil, so we have bs squared. First, outer, we have plus 3bs. Inner, we have plus cs. Last, we have 3c. Okay, group the terms. So we have as squared plus bs squared. Okay, and then next one is the s. So we have 3bs plus cs, and then the constant. So we have plus 4a plus 3c, and that is equal to 6s squared plus 50. So what are we going to do is to factor out, okay, s squared, we have a plus b, and to factor s here, s 3b plus c, and to leave this constant as it is. So that we can now rewrite our equation. So we have s squared, a plus b is equal to the coefficient of s squared, because we have s squared here that is equal to 6. And then we have 3b plus c. So since we don't have any s term here, the coefficient is 0. And then we have 4a plus 3c, which is equal to 50, okay, because it's a constant. So using these three equations, okay, we have equation 1, we have equation 2, we have equation 3, we can solve for the values of a, b, c. Okay, so from equation 1, what are we going to do? We have a is equal to, let's get a, so 6 minus b. Then we have, we're going to substitute this to equation 3. Okay, it's up to you as long as you get the values of a, b, and c correctly. So we have we have for the second equation from equation 2, okay, we can get that 3b plus c is equal to 0. We can get that in terms of c, so we have c is equal to negative 3b. Substitute also to equation 3. Okay, so if we do that, if we do this substitution to our equation 3, so we have 4 times 6 minus b, okay, plus 3 times negative 3b is equals 50. Okay, and upon solving this, okay, if we're going to solve this, we can get a value of b that is equal to negative 2. Okay, we have the value of b, and we can simply get the value of a from this equation. So we have a is equal to 6 minus negative 2, and that is equivalent to 8. Okay, so we have the values of a, b, and c now. So for letter c, negative 3b, from this equation we have our b is negative 2, so the value of that is 6. So our equation now, okay, partial fraction would now be equal to this. So we have 8 over s plus 3, because a over s plus 3. Then we have plus, okay, our b is negative, so negative 2s plus c, which is plus 6 all over s squared plus 4. And this is actually equal to the y of s. Okay, recall that. That's equal to y of s. So we can now simply get the Laplace transform or inverse Laplace transform, okay, of y of s in order for us to get the, okay, y of t, which is the solution to our differential equation. Okay, so if we're going to get the Laplace transform of that, inverse Laplace transform of that, so inverse Laplace transform of y of s, okay, so we have inverse Laplace of 8 over s plus 3, and then we have plus the inverse Laplace of negative 2s plus 6 all over s squared plus 4. We know that this is very easy, okay? So we can factor out 8 outside of the inverse Laplace and evaluate this. The Laplace transform of 1 over s plus t would become e raised to negative 3t. 8 times e raised to negative 3t. Okay? For this one, for this term, we can further simplify this. Okay? So we have the Laplace transform. Okay? I can factor out this. So we have negative 2. Okay? I can separate the numerator. Okay? I can separate the numerator. So we have 2s. Please bear with me. So we have inverse Laplace of negative 2s over s squared plus 4. Okay, plus, okay, the inverse Laplace of 6 over s squared plus 4. So we can factor out the constants. Okay, constants outside of the my mistake, this should not have any negative because this is the negative already. Okay, so we have negative 2 Laplace transform of s over s squared plus 4, for inverse Laplace plus 6, the inverse Laplace of 1 over s squared plus 4. Okay, getting the inverse Laplace of that is simply 8e raised to negative 3t, and this is simply cosine. So we have negative 2 cosine of the value of a. Okay, this is a squared, so we have 2t. And this is, we're going to multiply, make this multiply to 2 factorial over 2 factorial because we want this, I'm sorry, not factorial, just only 2. Okay, 2 over 2 because we want this numerator to become 2 in order for us to evaluate its Laplace. So we offset a value of 2 over 2 so that we can evaluate the Laplace of this, which is to be sine. So we have negative 2 cosine 2t. So we have plus 6 over 2. Then the inverse Laplace of 2 over s squared plus 4. Then we have 8e raised to negative 3t minus 2 cosine of 2t. plus 3, then this is now sine of 2t. Hence, our y of t or our solution for that differential equation is given by this. Okay? So we have y of t. Let me just rewrite it in red. So we have y of t is equal to 8 e raised to negative 3t minus 2 cosine of 2t plus 3 sine of 2t. Hence, we have already solved the given differential equation with initial value using the transform of derivative, Laplace transform of the derivative. So if you learn from this video, don't forget to give me a comment down below and don't forget to subscribe to my channel. And thank you so much for listening again. This is Engineer Abat. See you again on the next video.